Hi, I'm Herb Gross, and welcome to Gateways to Mathematics, where today we begin the subject matter proper of our course as we discuss Module 1, which is the development of place value. And one of the things that I would like you to really try to appreciate in this is that as we do the mathematics, we are going to be reliving, in a sense, the history of civilization. In our preface lecture, we talked about how different languages use different names for different objects, or for the same object. But basically what we didn't discuss was how did language come about in the first place? How were words chosen? How did we learn to communicate? The reason I bring this up is that basically throughout all of life, what we do is we talk about concepts, but all we see are words. And I'm going to talk about that throughout the course as we go along. It reminds me of the story of the little boy in Sunday school who said to the teacher, and Adam and Eve called the animal a hippopotamus because it looked just like one. Where do these names come from? How do we invent names? It's just an interesting concept. Think of something as simple as a pen. How could you even define what a pen was if there were no words invented yet? Try to think back to the dawn of consciousness and visualize what was going on this way. And the amazing thing is that once you invent a language, and we call these arbitrary or artificial languages, once you invent them, to the person who knows them, you can transmit tremendous sensations. You can transmit love, hate, jealousy, patriotism, tears, laughter, and yet to the person who doesn't know that language, it's conceivable that they don't know a thing about what's going on. And with that in mind, because we have a lot of things to discuss today, I want to show you how the language problem greatly affected the development of our system of arithmetic. And I call a subtitle of today's lesson, Some Arbitrary Languages. See, any language that's made up by people is called arbitrary or artificial. It's not natural. See, but some artificial and arbitrary languages are tough. And I underline the word tough to point out something that I find very interesting. People tell me that mathematics is very hard for them to learn. But yet, if you've learned to speak English, you have done something much harder than learning how to speak mathematics. Look at the O-U-G-H and all the different sounds it can make. With a T in front, it becomes tough. With a TR in front, it becomes trough. With a THR in front, it becomes through. If you put an O between the H and the R, it becomes thorough. If you put a TH at the beginning and a T at the end, it becomes thought. And if you put a DR at the beginning and a T at the end, it becomes drought. Look at that. The same combination of letters, 6 different pronunciations. You know, at least in math, we don't say it's pronounced 3 except after 7 when it becomes the. We don't do things like that. Once you've learned what 3 means, it's always the same thing. And you know, English just goes on and on and on this way. I remember seeing many years ago a little riddle in the Reader's Digest, and it said pronounce G-H-O-T-I, which could be goatee, whatever you want. Anyway, the answer to the riddle, as some of you may know, it's a classic, was fish. And what they said was, take the G-H as it appears in the word tough, see the F sound. Take the O as it appears in the word women, see O, but women, that's the I sound. Pick the TI as it appears in the word nation. See, fish. Look at all the different ways you can make the E sound in English. You can write receive, in which the E comes before the I. You can write believe, in which the E comes after the I. By the way, these are derivatives of the German, and in German, with the EI and the IE diphthong, that basically it's the last letter that's pronounced. In other words, with EI in German, it's always I. And with IE in German, it's always E. But look at the arbitrariness in the English language. How about the plain E sound in the word recede? How about the double E in the word read? And on top of that, what do we call them? Homonyms? Words that are spelled differently but pronounced the same? See, R-E-E-D is pronounced read. R-E-A-D is pronounced read. And that leads to an even more interesting case. What's the past tense of the verb read? It's read. And how is it spelled? R-E-D? No, R-E-A-D. Not only do you have different spellings for the same sound, In English, the same spelling can have different sounds. How about this word over here? Is it wind or is it wind? Wound or wound? As a noun, this is a bird called the dove. As a verb, it's the past tense of dive, and it's pronounced dove. I mean, it's amazing if you can learn English that you should have trouble with the language of mathematics. Yet the fact remains that mathematics does have its own artificial language. And the important point was that how do you think artificial languages began? One of our assumptions is going to be in this course that people sought the simplest solutions to any problems that plagued them. And they looked for more complicated solutions only when the simpler ones either stopped working or they became too cumbersome. The easiest ways to describe what you wanted was to draw a picture. So the early artificial languages were sign languages, such as the Egyptian hieroglyphics. And basically what happened was you drew pictures. That's what you meant by a sign language. And here's the interesting thing. See, people did not understand that numbers in the real world are used basically as adjectives modifying nouns. Have you ever thought about that? You see, you have never seen 2. Well, at least not as a noun. You've seen it as an adjective. You've seen 2 fingers, 2 people, 2 apples, 2 oranges. But the concept of 2-ness is very, very difficult to define. And by the way, that doesn't happen just in math. Think, for example, about time. We can measure time to the nearest billionth of a second. And we're going to talk a little bit more about that at the end of the program. Yet, no one has ever seen time. What we see are the effects of the passing of time. There are many things that we can talk about, that we can measure, that we can philosophize about, but we've never seen them. And one of the problems that we have in mathematics is that numbers are usually adjectives modifying nouns, and because we don't understand that, we sometimes miss the essence of the subject. Let me give you an example. Suppose this picture over here represented a person. See, the noun is now the picture. How many people are there in this picture? 2. See, and by the way, notice the pictures are kind of crude here. It doesn't tell you what kind of a person. They all look like very thin stick people. You can't tell what the sex is, and I'm not going to give you any clues. You can't tell if the person is tall or short, blonde or brunette. You see, you pay a price. We'll talk about that more as we go along. It's sort of like the little kid. He sees a horse, he calls it horsey. He sees a mule, he calls it horsey, because it looks like a horse. He sees a zebra, he calls it a horsey in fancy striped pajamas. But basically, the word horsey means a whole bunch of things to the kid. And you see, that is basically inherent in our sign language. See, 2 people. But where is the 2-ness here? You have to count them. 1, 2. See, what's over here? I've used different colors to indicate that people recognize these as different things. This is 2, well, I'll call them apples. They might be oranges, they might be pomegranates, they might be anything. But this is going to be the picture for an apple. So here I have 2 people, here I have 2 apples. The part that's interesting is, in both cases, the adjective is the same. But you see, the 2 apples don't look like the 2 people. Here I've drawn, I don't know what they are, let's call them doggies. I've drawn 2 doggies. And I've drawn them in blue because the doggies don't look like apples and they don't look like people. But where's the 2-ness? I count them. 1, 2. And it took people a long time. And it sounds so obvious now. But you know, it took a long time before somebody came around and said, why can't we just assume that the adjective has to be given, but the noun can be implicit? In other words, if we're talking about people, 2 will be understood to modify people. If we're talking about cows, 2 will modify cows. And what they discovered is they would draw a line called a tally mark, 1 for each object. So whether you were talking about 2 people, 2 apples, or 2 doggies, you made 2 tally marks. See, that was abstract. You had no way of knowing what was being represented now by the tally marks. And as so often happens, once you make an innovation, problems arise. Look, for example, at the person who's counting his doggies. Well, call them sheep in this case. Okay? One person has this many sheep, the other person has this many sheep. Who has more sheep and how many more? Don't go by which line is the wider, because notice that these are closer together. And pretend that you can't count. Remember, we're back at the dawn of consciousness. How could you decide which of these 2 represented the greater number if you couldn't count? you do what little kids do. They say, one for me, one for you. One for me, one for you. One for me, one for you. And by the way, if this sounds too childish, I'll give you the college level terminology for this. And that's called, we make a one-to-one correspondence. Kids are funny that way. You say to a little kid, take half of the candy, he doesn't know what that means. But if you say one for me, one for you, one for me, one for you, that he understands very well. So we keep on going this way. One for me, one for you, one for me, one for you. One for the top, one for the bottom, one for the top, one for the bottom, top, bottom, top, bottom. And if this sounds monotonous, it's supposed to be, because it's a difficult procedure. When I get all through, notice that I've done what? I've crossed out all of the tally marks on the top line, but I still have what? 2 tally marks left on the bottom line. Therefore, the bottom line had 2 more tally marks than the top line. And by the way, that is a genuine way of counting. Suppose I have a room filled with chairs, and a whole bunch of people walk in, and they all sit down with only one person to a chair, all right? When all the people are seated, let's suppose there are still some empty chairs. Without counting, I know that there were more chairs than people. See, because some of the chairs are empty, but everybody's sitting down. If everybody's seated in the chair, but some people are still standing, I have more people than chairs. And if everybody is seated in one chair, each person to a chair, and no chairs are empty, then I know what? I don't know how many people I have, I don't know how many chairs I have, but I know I have as many people as there are chairs. And that's the primitive version of counting, okay? But you see, what started to happen over here is even relatively small numbers became cumbersome. And let me show you some things that happened throughout history. If you have 200 cows, what do you call that collection usually? What's the name given for a bunch of cows? It's called a herd. So 200 cows is called a herd. What if you had 431 cows? That's still called a herd. See, a herd is a lot of bull. No, a lot of cows, okay? Now, what if you have 431 sheep? You don't call that a herd because sheep don't look like cows. You call that a flock. You don't call the guy who takes care of them a sheep flocker, but that's another story. In any event, look at how we do this with a whole bunch of things. Think of this. What did we talk about? Notice that when we have a lot, not only is it difficult to count, but we pick a different adjective depending on what we're counting. For example, we talk about a colony of elephants, a pride of lions, a bevy of geese, a school of fish, a swarm of bees, an army of ants. You see the kind of language that we have this way? And so what was the next innovation? People discovered that they had, in general, 10 fingers. And they decided to use 10 as a basis. In other words, somehow or other, you feel quite comfortable counting tally marks that you can see. So 10 became a very common number of tally marks to think in terms of. For example, going back to the previous problem, if we had taken the top row and agreed to segregate the tally marks in groups of 10, somehow or other, do you recognize the 14ness over here much easier? See, if you know that this is 10 without counting, this is what? 10 plus 4. 4 plus 10. Teen means plus 4. See, 14 is 4 plus 10. Actually, what happens is usually you don't know how many 10 is, so you usually count. See, 1 for each finger. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Then you cross out in bundles of 10. After a while, the Romans came up with a very interesting abstraction. They said, if you're going to cross out the 10 tally marks, why bother drawing them in the first place? If you're going to cross them out, why not just use the crossing out symbol to stand for 10? So now 14 became written this way. It was an elongated X and 4 tally marks. The Romans' next innovation, which was not that major, was they said, hey, this looks very much like a letter in our alphabet. So what they did was they contracted the crossing out symbol into the letter X. So X stood for 10. Now, I suspect that almost everybody watching this, either through grade school or watching what date the movie was made, knows that X stands for 10. Okay? What you may not realize is the beauty of this abstraction. There is no possible way of looking at the X and guessing that it stands for 10. For example, if I write down XXX, the one thing you can tell me for sure is that there are 3 X's. But unless I tell you that the X stands for 10, you don't know that that's 3 10s. You see, this is a major step forward. For the first time, a symbol does not look like the number it stands for. In other words, with the tally marks, you could count the adjective. With the X, you have to know that it stands for 10. For example, if we were born with, suppose we decided to count with only one hand, then the X might have stood for 5, in which case this would still be 3 X's, but now X would stand for what now? 5s. You see, it wouldn't be 3 10s, it would be 3 5s. So, for example, what the Romans were now able to do is look at this expression over here. See, the nouns are visible, the X's and the I's. The adjectives are implicit, you have to count them. See, what do I have here? 2 X's and 4 I's. X stands for 10, we've memorized that. That's 2 10s and 4 1s, that's 24. That's a lot more complicated than the way we write it, but remember, when you want to see what a society contributed to civilization, you don't judge them by what comes later. You judge them by what was happening before. What improvement did they make? And remember, before these symbols were invented, how would you indicate 24? You would have to write 24 separate tally marks. You see the improvement this way? Now what happened was the Romans decided they had hold of a good thing. Why keep more than 9 of any denomination? When we get too many X's, why can't we trade them in for something else? And so what they said was, we're going to use 10 as a trade-in system. And by the way, that's where the word decimal comes from. Dec is 10. Decum is 10 in Latin. So that's where the word decimal comes from. The word dime is a corruption of the word decimal. See, dime is a tenth of a dollar, 10 dimes to a dollar. But what they did was, is they took the letter C, that comes from the Latin word centum, which stands for 100, like the word century, right? Per cent, 100 cents to a dollar, per cent is per 100. A centurion, which was one of 100 elite Roman soldiers. You see, so 10 X's became replaced by a C, and since 10 tens is 100, C was the symbol for 100. And how do you learn that? You memorize it. And you say, well, how am I supposed to memorize all that? How did you memorize all the different ways to pronounce O-U-G-H and all the E sounds and make fish out of G-H-O-T-I? That's what we're doing here. You see, so now if you made 3 C's, this is interesting. The 3 C's don't look like the 3 X's that we just had before. But notice that the adjective 3 is the same. See, only now, see, before when you wrote this, the 3 modified tens. Now the 3 modifies hundreds. See, counting them gives you the adjective, the picture gives you the noun. So now when I write down something like this, how do I read it? I have 4 C's, 3 X's, and 2 I's. Now I've memorized that C stands for 100, X stands for 10, I stands for 1. This is 432, which is a tremendous improvement over having to write 432 tally marks. Do you see how this thing is working? Little innovations at a time. Now when they came to 10 C's, they decided, well, we'll make up a new letter. The Latin word for 1,000 was millum. That's where the word millimeter comes from, milligram, 1,000th of, okay? So M became known as the symbol for 10 C's. Since each C was 100, 10 C's were 1,000. See, now what happens is, when I draw the 3 M's over here, the adjective 3 is the same, but now it modifies what? 3,000. Say, I don't know if I'm making this clear to you, but in a sense, whether I draw 3 M's, 3 C's, or 3 X's, it's sort of like talking about herds, flocks, and bevies. In other words, the adjective is the same, but the noun becomes different because I'm talking about different denominations. But see how visible the adjective is over here? So for example, if I write down 4 M's, 3 C's, 2 X's, and an I, that's what? 1, 2, 3, 4, 4,321, which is a tremendous improvement over 4,321 tally marks. By the way, as I tell you this story, you get the feeling that progress was very, very smooth. Let me point out to you that sometimes there were modern changes made in an era that didn't help things, and you only could look back at it later to see what really happened. I call this hindsight is better than foresight by a darn sight, or newer isn't always better. That's another common mistake we make today. If we replace something by something new, we automatically assume that newer means better. and it's not always true. Let me show you a few of the things that the Romans did. For one thing, as we mentioned in our preface lecture, they noticed that half of the symbol x looked like the letter v. So they said what? Since half of x is v, half of the numeral x is the numeral v, half of the number 10 will become the number 5. So v denoted 5. And so now, rather than write 16 as an x and 6 i's, they wrote an x, a v, and an I. See, that was now 16. But you see, even though this was more compact, do you notice that this destroys the decimal property? See, up until now, it's always been what? 10 of one denomination equals 1 of the next higher denomination. But now it's what? 2 v's equal an x. That's what makes the English system of measurement so difficult. You have to memorize too many conversion factors. See, 12 inches to a foot, but 3 feet to a yard, and 1,760 yards to a mile. You see, these things become very, very cumbersome. The other thing that the Romans did to try to make things easier, and it made a mess out of things, was what we call the subtractive property. See, what the Romans said was, if you put a noun of a smaller denomination in front of one of a larger denomination, it means you subtract it. In other words, since x stands for 10 and c stands for 100, by putting the 10 in front of the 100, you read it as 100 minus 10. Sort of like saying 10 minutes before 6. Versus if you put the x after the c, then it's read as 110. See, it's like 10 minutes before 6 versus 10 minutes after 6. But you see, what made this thing difficult is that a c is always 100, an x is always 10. Why should the addition or subtraction depend on the placement? You see, what happens is, in terms of money, if you have a $100 bill and a $10 bill, it's still $110 whether you count the $10 bill first or whether you count the $100 bill first. So these were some of the problems we were running into. Now, why did people make a change? In other words, granted that newer doesn't mean better, there must be a reason why people want something new. For example, if a kid has never eaten carrots and has only eaten peas and says, I want carrots, you don't say, how come you want carrots? You've never tasted them. You say, well, since the only thing the kid has ever tasted is peas and he doesn't know what carrots taste like, it must mean that he wants something other than peas. So you give him spinach and he says the carrots are good. Or the carrots are still not good, whatever it happens to be. You see, what the Romans were really trying to do was to find a system to still make it easier to count. And the Egyptians had earlier come up with a system very, very similar to the Romans. See, I started with the Romans, even though the Egyptian is older, because the Roman system is the one you're probably more familiar with. What the Egyptians did was they recognized patterns. In other words, they didn't put symbols for 5, like V. What they did was, when they counted, they recognized that it was very easy to keep track of 3 or 4 at a time. So when they wanted to write 4, they would write, notice the psychological effect here, the 2 rows of 2 versus 1 row of 4. You notice that somehow you look at this and you can see the 5-ness much more readily than if all 5 were in a row. See 5, 6, 7, 8, 9. Do you notice how different 8 and 9 look this way? See 2 rows of 4 versus 3 rows of 3. We do this with dice. On a pair of dice, do you notice that when this comes up, you don't even bother counting the dots? You recognize the pattern. You say 5. And when this comes up, you don't say 1, 2, 3, 4, 5, 6. You recognize the pattern and you say 6. Actually, what the Egyptians did was exactly the same thing that the Romans did. Only, as usually happens, they had a different language. They used the tally mark for 1. For 10, rather than using what the Romans called X, they used what some archaeologists call an arch, other archaeologists call a heel bone. I don't really care what you call it. I call it an arch. But basically, the important thing is what? Just like the Roman numeral X, there was no way of looking at the arch and knowing that it stood for 10. See, and now if they wanted 5 tens, they just made 5 arches. See, 1, 2, 3, 4, 5. You just count the adjective. So now they did the same thing as the Romans did. When they got to 10 arches, they invented a new symbol. The symbol looks like a funny 9. Some people call it a scroll. Other people say it's a coil of rope. Again, I don't care which one you want to call it. This scroll stands for 10 arches, which are 10 tens or 100. So now if I write the 5, but the noun is now the coil of rope, it's still 5 over here as an adjective, but it's 500s. And then the symbol for 1,000, see 10 hundreds, was a lotus plant. I don't know where it came from, a lotus plant. But that was, in other words, the Egyptians used this the way the Romans used M, and the Egyptians used this the way the Romans used C. So now, when you drew the 5, but the noun was the lotus plant, it stood for what? 5,000. And just to show you how easy this is, I'm going to let you read this number for me. I'll read it out for you so you see what I have here. I just hope somebody of importance doesn't walk by and think I'll flip my lid. You have a lotus plant, 9 coils of rope, 8 arches, and 5 tally marks. What is that? It's 1,900, 8 tens, and 5 ones. The year in which this lecture is being given, or at least started. We never know when one of my lectures is going to end. We'll just see, this is the year 1,985. And as cumbersome as that looks, isn't that a heck of an improvement over 1,985 separate tally marks? The next innovation came when people said, look, this is real neat, but every time we come to 10 of a denomination, we have to invent a new symbol. And the way they solved that problem was even 10,000 years earlier in the Far East. And in the Middle Ages, in Western civilization, we called it the sand reckoner. In the Far East, they called it the abacus. Rather than drawing different pictures, well, the sand reckoner was you just drew lines in the sand. And the line furthest to the right stood for ones, the next line for tens, hundreds, thousands, etc. And if you were a Roman and you wanted to read this, this was what? The I's, the X's, the C's, the M's. If you were an Egyptian, it was the tally marks, the arches, the coils of rope, and the lotus plant. But this was a place value. In other words, the nouns are still visible, but they all look alike, don't they? The only way you can tell them apart is by where they're placed. And what people did is they took pebbles, stones. The stone now became the adjective. See, wherever you placed that one stone, it was always one stone. But what it modified depends on where you placed it. If I put it here, the stone meant 1,000. If I put it here, it meant 100. If I put it here, it meant a 10. And if I put it here, it meant a 1. Here, I've put a few stones down here. How would you read this? There are 2 stones on this line. How do I know? I counted them. How many stones on this line? 1. How many stones on this line? 3. So what do I have altogether? The nouns are ones, tens, and hundreds. So I have 200, 10, and 3 ones. That's 213, which of course the Romans would write as CCXIII, and the Egyptians would write as 2 coils of rope, a notch, and 3 tally marks. But do you see the innovation here? You see, I don't have to invent new symbols. And in fact, I just thought you might like to see something. The difference between the abacus and the sand reckoner is that when you took this thing and you encased it and replaced the stones by beads on the wires, then that became a portable sand reckoner, which is the abacus. And in fact, if you'd like to hear something that's even more interesting from my point of view, do any of you happen to know what the Latin word for stone or pebble is? I think this is exciting. It's calculus. Calculus means stone. Well, not exactly as a noun, as a verb. It does. You don't say a guy went out, had a good time, and came home calculus. You don't say that, okay? But in a sense, calculus means stone. And in fact, the word to calculate means to do arithmetic using stones. And here today, in terms of language, we think of calculus as being a very advanced subject. All of mathematics is calculus. In the subject called calculus, we calculate something special that we don't calculate in other math courses, but calculus is still calculus. In a sense, if this course seems elementary to you, we can call this Calculus 1. It's the beginning of all calculation courses, okay? And again, I want you to notice the beauty of what happens when nouns are present. You see, what happens over here is, let's read the abacus or the sand reckoner in this case. What do I have here? I have 2 pebbles on this line. What line is this? Ones, tens, hundreds, thousands. So I have 2 thousands. Now, how many hundreds do I have? None. How do I know there are none? Because this is the noun for 100. If I had any hundreds, there'd be stones there. See, I have what? 2 thousands and 1 10. In much the same way as the Roman would have written 2 M's and an X, and the Egyptian would have written 2 lotus plants, and a notch. The reason I bring this up is that this is a form of place value. But what makes this place value different from our own Hindu-Arabic derived place value is that the nouns are still visible. See, even though these lines still look alike, they are visible. We can see that there are no ones. We can see that there are no hundreds. Now, in the system that we use, we go one step beyond. The Hindus came up with 9 basic characters to start with. Those characters were called digits. And by the way, the word finger or toe became known as a digit also, because you see, for numbers that were no more than your fingers and in some cases your toes, you could count them very easily. See, if you wanted like 27 plus 5, you just held up 5 fingers, 28, 29, 30, 31, 32. See, digits were very, very easy to handle. Now, basically what they did was, you say, well, this is strange. These digits don't look like the numbers they represent. They're not supposed to, any more than the X looks like 10. What was amazing about this, though, was that each digit, by virtue of where you placed it, named the denomination. See, the digit furthest to the right was the ones, the next digit was the tens, the next digit was the hundreds. So when you wrote 2, 3, 4 this way, you see it was what? 4 ones, 3 tens, and 2 hundreds. We would read this as 234. Now suppose I scramble the digits, and I change the order to 4, 2, 3. This is now read as 423, because this is what? The ones digit, the tens, and the hundreds. You see, as long as the nouns are visible, there's no problem. When the nouns become invisible, you see, there are no letters of the alphabet here, there are no lines in the sand here. See, here's the thing I want you to see. How would the Roman have written 234? It would have been 2 C's, 3 X's, and 4 I's. And when he wanted to write 423, there would be 4 C's, 2 X's, and 3 I's. Somehow or other, the fact that there's a 4 here and 4 here doesn't bother you, because it's clear that the 4 is modifying C's here and I's here. You see, when you can see the nouns, you can, well, in terms of money, if you have a bunch of bills, you can shuffle them. That doesn't change the value of the bills. See, the same on the abacus. How would you write 234? You'd put 2 on the 100 lines, 3 on the tens lines, 4 on the ones line. See, 234. Because the nouns are still visible. See, what would 423 look like? 4 hundreds, 2 tens, and 3 ones. Do you see the idea here? Now, here's where the real problem comes in. Here's where the serious side effects come in. Suppose I wanted 2 hundredths and a 1. See, how would you read this number over here? It's 2 hundredths and a 1, isn't it? The Romans would write that as what? C, C, I. This is 2 thousands and 1 10. The Romans would write that MMX. This is 2 hundredths and a 10. That's 2 C's and an X. This is 2 thousands and a 1. That's MMI. As you look at the Roman numerals here, is there any danger, if you know the Roman numerals, of confusing these? No, because the nouns are visible. You know that there are no 10s here, because the noun for 10 is X, and there are no X's here. You know that there are no hundreds here, because the noun for 100 is C, and there's no C here. The problem comes up in our place value system. How would you write these numbers if you left the nouns out? What are you going to say? I have 2 hundreds, I'll skip the tens place, and I have a 1. I have 2 thousands, I'll skip the hundreds place, I have a 10 and no ones. I have 2 hundreds and 1 10, and I have 2 thousands, no hundreds, no tens, and a 1. Do you see how confusing this looks? What we have to do is, because the only way we can tell what the noun is by where the digit is placed, we have to give us indication of what nouns are being skipped. So over here you say what? I have a 1, skip the tens and 2 hundreds. I have no ones, a 10, no hundreds, and 2 thousands. See? I have no ones, a 10, and 2 hundreds. I have a 1, no tens, no hundreds, and 2 thousands. And the symbol that we invented to take the place of the placeholder was what we call a 0. And you see, 0 becomes the 10th Hindu-Arabic symbol. See, 0 is the 10th Hindu-Arabic digit. It's a placeholder used when there are none of a denomination. And why is that? Because up until place value, the nouns were always visible, so the absence of the noun meant that you had none of that denomination. Let me show you an even worse problem over here. How much is this number here? I put it in quotation marks on purpose to make a point. This number looks like 213. But how do you know it wasn't 2 10s and 13 ones? See, for example, in Roman numerals, if I wanted to, could I write 2 x's and 13 ones? Sure I could, but I didn't have to. I could trade in 10 ones for an x if I felt like it. If this bothers you, think in terms of money. If I have 2 $10 bills and 13 $1 bills, okay, that's $33 regardless of whether I agree to trade in 10 ones for a 10 or not. But you see, in place value, since the nouns are no longer visible, I must restrict myself to what? 1 digit per place value column. We're allowed only 1 digit per place value column to avoid ambiguity. And now what's interesting is a version of the more things change, the more they remain the same. Sometimes when we cure a problem, we advance to such a stage that we suddenly realize, hey, we didn't cure this, we just put it into remission. Let me show you what happens now after we've come up with this enormous discovery called place value. Now I say to you, what number is named by, and look at all these digits, 1768329466791. What number is named by that? Well, here's where we borrowed from the Egyptian again. Remember the Egyptians said you could keep track of a certain number of symbols at a time? Look at the number 643. Let me ask you this. When you look at the number 643, do you say, let me see, the 3 is in the ones place, the 4 is in the tens place, the 6 is in the hundreds place, or do you read this as 643? It's relatively easy to keep track of digits 3 at a time. We know this is what? Without even counting, we say what? 643. Here we say 346. See, we're used to ones, tens, and hundreds with no troubles at all. And notice that with ones, tens, and hundreds, without using more than 9 of any denomination, you can get up to what? 999. The problem is you have too many denominations over here. So what we did was we decided, okay, people can keep track of numbers up to 1,000 very easily. So what we're going to do is the following. When you take all these digits, start at the right, and break them down into batches of 3s. And the first group of 3, see what I'm saying? You have ones, tens, and hundreds, and they're going to be called units, okay? The next group of 3 are going to be called thousands. So now you still have ones, tens, and hundreds, but this is what? 1,000, 10,000, 100,000. The next group becomes known as millions, okay? Next group becomes billions. And the way you want to learn that word is that billion is bi, by. Think of this as by million. See, a billion is by million. See, a million, million. Trillion is tri-billion. See, trillion. After trillions, the next noun would be quad for 4, quadrillions, then quint for 5, quintillions. We're not going to worry about that right now. But you see what I'm doing over here? I'm breaking the number into groups of 3 digits each. The first group of digits are called the units, and basically we don't pronounce those. When this whole messy, see, if we're talking about a whole mess of things, maybe it's seconds, maybe it's grains of sand, maybe it's people, the units take on the name of what you're counting. Like you say, 62,876,917 grains of sand. See, the units are what you're counting. But these are the units, the next 3 are the thousands, next 3 the millions, next 3 the billions, next 3 the trillions. Now that's some more vocabulary, isn't it? But you learned English, so you can learn this vocabulary. And here's what we do next. See, what we do is we take that long, messy number that I gave you, and I want to show you the beauty of this. I want to show you how elegantly, by learning a good, strong artificial language, you can learn to communicate in a way that you can't when your vocabulary consists of horsey and doggy and stick people, okay? See, what I do is now, instead of putting in these bars for digits of 3s, I use commas instead. See, I segregate these in groups of 3s. Now, I'm going to write these in, but ordinarily we memorize these. See, the first group are going to be the units, then there's going to be the thousands, the millions, the billions, and the trillions. Now, do you see how you read this? What's this number? 17. 17 what? 17 trillion. What's this number? 683. 683 what? Billion. 294 million. 567 1,941 units. You see, your adjectives are never more than a 3-digit number. You get the idea here? If you learn these nouns, you break this down. And in fact, you can do the thing in reverse. Suppose I say to you, write as a place value numeral, and this scares a lot of people. And I'm not even talking about people who have English as a second language, English as a first language too. 47,086,937,000. See, this is a game where we go after big fish. What are the nouns we're looking for in this game? Units, thousands, millions, billions. You see, ones, tens, and hundreds we don't go after. So what we look for are key words. Here's the word trillion. Here's the word billion. Here's the word thousand. What nouns, what adjectives modify these nouns? 47. Do we know how to write 47? Sure we do. What noun modifies billion? 86. Do we know how to write 86? Sure we do. And what noun modifies thousand? What adjective modifies thousand? 937. 937. See, we don't have to keep track of more than 3 digits at any one time. See, now what we do is we go back to this diagram over here, and we put in what the required numbers are. See, how many trillion do we have? 47. Remember, 7 ones and 4 tens. So we write 47 trillion. How many billions do we have? 86. So the 6 goes in the 1 billionths place. The 8 goes in the 10 billionths place. How many millions do we have? None. How do we know that? Because the noun millions was missing in the description. How many thousands did we have? 937. How many units did we have? None, because the problem ended after the word thousand. So in other words, this is what this looks like. But remember our agreement. What we're going to do is we are going to leave out these labels, we're going to leave out the dashes, and we're going to put commas in. The problem is, once we agree to do that, we no longer have a visible way of keeping track of our denominations. So every place where nothing was there, see, we don't have to put the 0 in here now because the blank is empty. But if I'm going to erase the blanks, I have to make sure I have placeholders in here. And so I write this now as what? 47 trillion, 86 billion, I'm skipping the millions, 937,000, period, no units. Don't write this. In other words, in this comma situation, there must always be 3 digits between commas, except of course at the very end, because there may not be enough. But I'm saying, as you're reading from left to right, between every pair of commas, there has to be 3 digits. You see, when I write this, I don't know whether the 8 is supposed to be in the hundredths place or in the tens place. See, how do I know? See, is this 860 or is it 86? So to indicate what I want here, I would put the 0 here. If I put the 0 here, that would have been 860 instead of 86. And don't omit blocks of zeros. Don't say, well, this is nothing, I'll just chop it off. Because look what happens if you chop this off. If I chop off these 3 zeros, as an adjective, this is still 47. But what's it modifying? Units, thousands, millions. What was this adjective supposed to be modifying? What was this adjective supposed to be modifying in the problem? You see, if I leave out the blocks of zeros, the 47 becomes millions when we were told it was supposed to be what? Trillions. See, the 47 is the same, but you don't know the number till you also know the noun. See, a yellow shirt doesn't look like a yellow boat, even though the adjective yellow means the same in both cases. The 47 is the same, whether you say 47 million or 47 trillion, but you need the noun in there. And then I write this little phrase here, and the beat goes on. Remember what started this whole problem? What started this whole problem was the tally marks became confusing to read. What happens now? Now we can deal with numbers that are so big that it becomes difficult to read the number of zeros. These are enormously large numbers, but just counting the zeros here is as complicated as counting the tally marks when we get started before. So we invent an even newer notation. What we do is to indicate that we're going to have a 1 followed by zeros, is we write a 10. That's called the base, all right? Then above the 10, we write a small 4. That's called the exponent. And this is read 10 to the 4th power, and it's called the 4th power of 10. And what this tells us is, and this is an easy way to remember it, circle the 0 and the 4. This indicates a 1 followed by 4 zeros. See, a 1 followed by 4 zeros. That would be 10,000. What would this number be? It's a 1 followed by no zeros. That's 1. What would this number be? It's a 1 followed by 1 0. That's 10. What's this number? It's read 10 to the second power. It's a 1 followed by 2 zeros. That's 100. Now we get into the heavy stuff. Remember we said the zeros were hard to keep track of? See, how would you read this number? It's 10 to the 13th power. That means what? A 1 followed by 13 zeros. So you put down the 1, put down 13 zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Now you come back this way with your commas at every 3 digits. This is what? Units, thousands, millions, billions, trillions. This takes the place of having to write 10 trillion. And now, you know, the top number I wrote when we started this board was a 1 followed by 19 zeros. And see, how would you write that now? A 1 followed by 19 zeros is simply 10 to the 19th power. And a 1 followed by 22 zeros would be a 10 to the 22 power. You see, it's hard to count 19 zeros versus 22 zeros, but it's easy to look at the exponents and say, oh, this is a 1 followed by 19 zeros, and this is a 1 followed by 22 zeros. And one of the problems is, when we start to throw around big numbers like this, we forget how impressive big numbers are. You know, see, with tally marks, numbers like 1,000,000 and 1,000,000,000 are overwhelming. And in today's technology, numbers like millions and billions are chicken feed. Just look at the next budget that comes out. But basically, I thought you might like to see something about relative size. How big is a billion? How big is a million? A billion seconds is 31 years. A million seconds is only 12 days. A million is to a billion as 12 days is to 31 years. People say something like, the government spent either 14 billion or 14 million. I can't remember which. And that makes as much sense as a person saying they either sentenced them to 31 years or 12 days. I get mixed up. See, that's how profound this difference is. These are already huge numbers, but look how tiny they are in today's technology. And by the way, if you want to see something interesting about relative size, a million is small only compared to a billion. Let me show you how big a million is. Can you guess when the millionth day was since the birth of Jesus? How old were you when you became 1,000,000 days old? You should only live to become 1,000,000 days old. Do you realize that it has not been 1,000,000 days since the birth of Jesus? Do you realize that there will not be 1,000,000 days till the 26th century after the birth of Jesus? Look, let me give you a quick estimate. Suppose there were 400 days in a year instead of 365. And suppose this was the year 2000 instead of the year 1985. I'm going to go into Module 3 now, so for those of you who want to stay in suspense, cover your eyes while and your ears while I finish this. Remember the way to multiply this? We discussed this in Module 3. 4 times 2 is 8. There are 1, 2, 3, 4, 5 zeros. In other words, if this were the year 2000 and there were 400 days in the year, there would only have been 800,000 years, 800,000 days since the birth of Christ. Isn't that an amazing number? But now if you want to see a real amazing number, let's switch to a subject called chemistry. I'm not going to give you scientific applications too much in a course like this, but I do want you to see how beautiful mathematics is. I want to show you that in the creative scientists, there is as much creative poetry as there is in a writer like Shakespeare. In fact, in a certain sense, there's even more in the scientists. Because no matter how flowery the scientist's theory is, if it doesn't work, we say things like, well, I could invent a theory too if it didn't have to work. But when Shakespeare writes Romeo and Juliet, you don't say things like, well, I don't see why they had to die over it. You say, yeah, but the beauty of the thought, the beauty of the expression. See, the scientist must not only be creative and beautiful and see things in unique ways, it has to explain the world. Contrary to what most people think, science is not cut and dry. It is a very dynamic. In fact, one of the reasons I think that people don't fully appreciate math and science is that too many of us as teachers forget to tell it like a love story. But let me show you something from chemistry that's really mind-boggling. And this goes back to the late Middle Ages. This is not modern. There is a number called Avogadro's number in chemistry. It's written in this form, 6 times 10 to the 23rd power. And all this does is it puts a 6 in place of the 1. In other words, if you want to know what this number looks like in terms of place value, this is a 6 followed by 23 zeros. Do you know how big that number is? I just showed you how big a billion was, right? To count out this number, if you could count a billion per second, it would take over 1,000,000 years to count this number. Is that a mind-boggling number? You bet it is. But do you know what Avogadro tells us? And upon this, many chemical and kinetic energy theories are based. That is the number of atoms there are in a little bit over a half ounce of water. In fact, if you want to be specific, this is the number of atoms in 18 grams of water. And if the word grams bothers you, relax, because in module number 10, we're going to take care of that problem too. But basically, this is a beautiful scientific story over here. Avogadro's number, 6 times 10 to the 23rd, a 6 followed by 23 zeros. A number that if you could write 1 billion tally marks per second would take over 1,000,000 years to write. And it's upon stuff like this that the universe is built. You see, you can't ignore science, because without science, there would be no high state of civilization. Science, in a sense, is the watchdog of sociology. It's science that allows us to have the weapons that we have to make decisions on whether we should use or whether we shouldn't use. But the same science that gives us the atomic bomb also gives us the polio vaccine. And so somehow or other, as we learn this material and we see it in excitement, let's relate it to the rest of our knowledge. Let's relate it to the fact that this is only one more topic that we will add to that whole arsenal of things that we need to make those decisions that's going to make the world a better place in which to live. And I think that's enough for our first introduction. You have plenty of work to do now, in a sense. I want you to read Module 1, do the study guide, work through exercise set 1, Form A, come back to see me if you have any questions on our next tape when we do Form B. But as we said in the preface, until that time, work hard, have fun, and stay young.